Can you see my screen now? Okay, so today we will do this type of questions. We have beams, like this one, we have a beam AB, and we have two applied load at point C and D. And the requirement is to find the shear force and bending moment at point C and D. Okay, so I will do point C and will give you some time to do point D. Okay, so now I will share other screen. Okay, here we have the beam. So question one. We have a beam AB, and we have roller support at A, hinge support at B, and we have the total span of this beam is 800 millimeter. We have two applied load, one here at point C and one here at point D. The load at point C is 800 newtons. The load at point D is 1500 Newton. The distance from A to C is 125 millimeter, 600 millimeter, and 75 millimeter. This is the beam AB and the loads and the distance. What is the first step to calculate the reactions? Sorry, what is the first step to calculate the shear force and bending moment at point C and D? What we need to do first? The first step is to find or calculate the reactions. How many reactions we have in this beam, for this beam? We have two supports, roller support at A. If we have roller support, so we have one vertical reaction, we call it YA. And at B, we have hinged support, so we have two reactions, XB and YB. So we have three reactions. So now we can start. Our first step is to find the reaction. Okay. So how can we find this reaction? If we apply the equation, the equilibrium equation, we have first equation, summation forces in x direction equal to 0. So XB, because we don't have any horizontal forces, so XB should be 0. So XB will be 0. The next equilibrium equation we have is summation moment at point A should be 0. If we are at A, what cause moment at A? If you are at A, so YB will rotate in this direction, will cause moment in this direction. 1500 will cause moment in this direction. 800 will cause moment in this direction. And YA will not have any moment for this case. So if we apply the moment at A equal to 0, we have YB multiplied by distance, which is 800 millimeter, and it is rotating anti-clockwise, so it is positive, minus 1500, the force, multiplied by the distance, which is 725 millimeter, rotating clockwise, so it is negative, minus 800 Newton, multiplied by the distance 125 millimeter, rotating clockwise, so it is negative. All this should be 0. Okay, from this equation, we find that YB will be positive 1484 Newton. Okay. Do you have a problem in this one? If you can check, if you can calculate and check my answer. Okay, can you check the answer for me? Okay, the answer is 1484.38 Newton. So this is the answer for YB, and the positive sign means that the reaction YB is going up. So YB is 1484.38 Newton going up. Now we can find the reaction YA using the third equilibrium equation. Summation forces in Y direction should be 0. What forces we have in Y direction? We have 800, 1500, and the reaction YB. So we have YB going up plus 1484.38 going up. So these two are positive. Okay, minus 800 going down, minus 1500 going down. This should be 0. From this equation, we can find YB equal to 815.63 or 62 Newton, and also positive. What does this positive sign mean? The positive sign means that also YA is going up. So YA is 815.62 Newton. This is the two reaction. So now we finalize the first step and we find the reaction. We have the reaction again, XB equal to 0, YB equal to 1484.62 Newton, and YA equal to 815.62 Newton. Okay, so this is the three action we have. And now we can go to the next step. Okay, so I will save this one. Okay. Now, the second step after reaction is determine shear force and bending moment at point C. To calculate the shear force and bending moment at C, I will draw the beam again. This is our beam again. Roller support at A, this B, hinge support. The reactions we have here 815.62 Newton. The reaction here is 1484.38 Newton. We have two forces. One here is 800 Newton. one here is 1500 Newton. The distance one to 5 millimeter, 600 millimeter, and 75 millimeter. Okay. The requirement is to find the shear at this point, shear and moment at these 2 points, C and D. Okay. To find the shear force and bending moment at point C, we need to have 2 cuts at point C. So firstly, we will have 1 cut just before C, and if we are coming from left, so 1 before C and 1 after C. We will call this one C left to at point C from the left, and this one point C right. So at point C, we will have 2 sections or 2 cuts, C left and C right. The difference between C left and C right is applying the 800 Newton. So C left and C right is to see the effect of applying the load 800 Newton. So if we need to calculate the shear force and bending moment at a section, first, why he choose C and D? He choose C and D because C and D has applied load. And if you want to calculate the shear and moment at a section, you need to make a cut just before the force and after the force. So we have 2 cuts at each point load. Okay. So now we will start with C left. If I cut at C left here, we will have 2 parts. So we have left part and right part. Which one has less forces or easy to deal with, the left part or the right part? The left part. So I will only work on this part because it has less forces. It only has 1 force. So I will do this part only. It is easier for us. So if I take this part here, this point A, roller support, and at A we have a reaction 815.62 Newton, and we have here our cut C left, and when we cut, the straining action or the internal forces appear. When we cut, what we will have, we will find that we have something called QCL or shear at point C left from the left. Okay. Another thing we will find is the moment. So we will have a moment at C as well, which we call MC left. So you need to know this one of the notes here. Any cut, if you have a simple beam, if you cut at any section of the beam, at any section of beam, you will have 3 main things: normal force, shear force, and bending moment. N for normal force, Q for shear force, and M for moment. Okay. For this section or for this beam, because we don't have any horizontal forces, so the normal is 0, but we will have shear and moment. Okay. Why we don't have normal and we have shear and moment? Because normal force mean the force perpendicular to the section. If this is our section, so the force, if the force is normal to the section or perpendicular to the section, this means normal force. If we have this section, so the force parallel to the section cause shear. Okay. And if we have shear, so we have moment because the moment is the integral of shear or the area of shear. Okay. That's why when I cut here, we have 2 straining action unknowns for us, QCL and MCL. And that's why the question asks for shear force and bending moment at C. Shear force is QC and bending moment is MC. Okay, so now we return back to section C left. If we cut a part of the beam like that, this part should be under equilibrium. How can this part be under equilibrium? If you can tell me. Under equilibrium means the equilibrium equation are valid. So what equilibrium equation we can apply here? The first equilibrium equation is summation forces in y direction should be equal to 0. What internal forces, what vertical forces or y forces we have here? We have 815.62, which is the reaction is going up, so positive. And what else we have? We have QCL minus QCL going down. Why assume it going down? You can assume it going up, doesn't matter. But I assume it going down because this part should be under equilibrium. So I have only one force going up. So the unknown should be going down to make equilibrium with the force, okay? With the reaction force. So we have the reaction going up and the shear going down. These two together should be equal to 0. So from this equation, we find that the shear force equal to positive 81562 Newton. So what is the shear force at C left? 815.62 Newton. Okay. Do you have any problem for this one? Okay, now we go to the moment. For moment, we will apply the equilibrium equation, summation moment at C should be 0. So to get the moment at C, we will apply summation moment at C should be 0. If we are at C here, at point C, left here, what cause moment at C? The shear force here, this shear force is passing through the no point, so it doesn't have any moment. So we will have MC left and 815 multiplied by the distance. This distance is equal to 125 millimeter, and this force rotating this direction. That's why I assumed MCL is rotating anti-clockwise, because I know that 815 will rotate clockwise. Okay, so if we apply this equation here, we will have 815.62 multiplied by the distance 125, rotating clockwise, so negative, plus MCL rotating anti-clockwise, so it is positive. This give us should be 0. From this equation, we will find that MC left will be positive 101,952.5 Newton millimeter. This is the moment at MC left. Or if we want to make the number a little bit small, we can divide by 1000, so it become MC left equal to plus 101.952 Newton meter. Okay. So now we find the moment and shear at MC left. Do you have any problem in this one? Do you understand this one? Okay, good. So now we continue to section C right. Okay. If you have a look on C right, this is our beam, part of our beam. We take this part only, A, and this is point C. This one was M, this is C left, and we have after C left, now we will have include the force with us, because in C left we didn't include the force, 800 Newton. So now we are at section C right. So I will remove section C left now. Okay. Okay. And don't forget that we have a reaction here, which is 815.62 Newton. Okay. Now when we cut at C, right, we will have? We will have shear Q, C, right, and also a moment M, C, right. Because if you cut in a beam, you will have to show the string action or the internal forces, which is MC right and QC right. Okay, with same procedure, this part of the beam need to be under equilibrium. Okay, so the first equilibrium equation we have is summation y equal to 0. What is forces in y? We have the reaction, and now we have 800 and we have QCR. So these three forces will be under equilibrium using equation sigma y equal to 0. So we will have 815.62 going up, so it's positive, minus 800, the applied load going down, so negative, minus QCR going down, I assume it going down. These three forces together should be 0. So if you have a look here, these two together will give us plus 15.62 Newton. So from this equation, QCR will be positive 15.62 Newton. So what is the shear at C right? How much is the shear at C right? 15.61. So the shear at C right is not equal to the shear at C left, because the shear at C left was 815.62 Newton. The shear at C right was 15.62 Newton. So what is the difference between shear left and shear right? Shear left and shear right, if you notice, what is the difference? What caused this difference? The force causing this difference is the point load 800. So the point load causing a drop in shear or a difference in shear between section left and section right. Okay. The second step is if we apply summation moment at C equal to 0. This to find the moment MC right. How can we find the moment MC right? If we are at point C here and take the moment, the equilibrium of the moment at point C. What cause moment and what doesn't cause moment? 800 will pass through the section, so it doesn't cause moment. QCR also passing through the section, so it doesn't cause moment. So only the reaction and MCR are affecting the equilibrium equation. So if we apply this one here, so we will have 815.62 multiplied by the distance. This distance is 125 millimeter. So 125, and I will give it negative sign because this one is rotating anti-clockwise. Sorry, clockwise. The moment MCR is rotating anti-clockwise, so I will give it positive sign. So MC right equal to 0. From this equation, MC right will be 101 952.5 Newton millimeter. Okay, and if you want to make this number a little bit smaller, so MCR will be 101.925 Newton meter. Okay. So what did you notice from MCR and MC lift? We can notice that the moment at MC left equal to the moment at MC right. Both of them is 101.925 Newton meter. This means that at any point, the moment left equal to the moment right. Okay, so the shear left different from shear right, but the moment left is equal to the moment right. This is the notice from this example. Did you understand this example? Do you have any question for the shear force and bending moment at point C? Do you have any questions? Okay, thank you. So now I will give you 10 minutes to try point D. So we need to calculate the shear force and bending moment at point D, left and right. Okay? And please try it and I will see what you have done. Thank you. Okay, for section D, or for, you can make it for point D. If I cut at D, this will be the cut. Or again, this is the beam. This is the whole beam first. Okay. And we have the reaction 815.62 Newton and 1484.38 Newton. And we have two applied force here, 800 Newton and 1500 Newton. Okay. And the distance is 125,600 and 75 millimeter. Okay, and this one is point D and this one is point C. If you want to find the shear force and bending moment at point D, we will do two cuts. One cut D left, one cut D right. If we do the cut at D right first, we have these two parts. Which part is easier for us to deal with, the right part or the left part? I think with the number of loads on the right part is much easier because we have only one load. So I will start with section D, right? And if I use this part, take this part out, so we will have the reaction here. 1484.38 Newton. And this is our cut, D, right? And we have here the force 1500 Newton. When I cut at D right like that, we will have a shear force QD right and a moment MD right. How can we find QD right and MD right? If we apply same procedure, summation y equal to 0, so we will have QDR going down negative plus the reaction 1484.38 going up positive should be 0. From this equation, the shear at D right will be negative or positive 1484.38 Newton. So this is the shear force at D right. We can apply summation moment at D to get the moment MD right. So if I apply the moment at D here equal to 0, so 1500 doesn't have moment, QDR doesn't have moment, so we will have only the reaction and MDR. So if we apply this equation here, so we will have negative MDR rotating clockwise, so I give it negative, plus 1484.38 multiplied by the distance, which is 75. This distance is 75 millimeter, should be 0. I give it positive sign because it is rotating anti-clockwise. This one is rotating anti-clockwise. So from this equation, we will find that MD right will be one 328.5 Newton millimeter. To make it smaller, we'll divide by 1000, so it will be 111.328 kilonewton meter. So this is the moment at MD right. If we want to do MD left, so section D left. For section D left, if we take section D left here, this is the reaction. 1484.38. This point D. And this section just after the force D left. And here we have a force applied here is 1500 Newton. The distance is 75 millimeter. And when we make this cut, we will have a shear force QD left going down, and we will assume the moment in this direction MD left. How can we find MD left and QD left? Same things, we apply summation y equal to 0. So we will have these three forces in y direction. So we will have 1484.38 going up positive, minus 1500 going down negative, minus QDL going down negative. This should be 0. From this equation, you will find that QDL will be 15.62 Newton. Okay, and negative because these two together will give us negative 15.62. So it will be in negative. Negative sign means that the shear should be going up, not down. Okay, the reverse direction. The second step, to find the moment at D left, we will apply the moment at D equal to 0. So if we are at D here, this force doesn't have moment, this force doesn't have moment, so we will have the reaction and MD left. So MD left, negative because rotating clockwise, plus this force rotating anti-clockwise, so plus 1484.38 multiplied by the distance 75, and positive because it's rotating anti-clockwise, this should be 0. From this, we will find that how much is the moment you expect. It will be 111 .328 111.328.5 Newton millimeter. And to make it a little bit smaller, we will make it 111.328 Newton meter. I just divide by 1000 to make the number small. Okay. Again, from this section, we notice that QD left does not equal to QD right, and MD left equal to MD right. So for the moment, you don't have to do left and right, but for shear, you have to, because MD left is different from MD right. Okay. Do you have any question for this example? So now we finish the shear and moment for point CD in question 1. And now I will shift to another example to calculate the shear and bending moment. Okay. For uniform distributed load. Can you see this example now? Okay. This example is same idea, but we have UDL, uniform distributed load, equal to 5 kilonewton per meter. And we have here, if you can see here, what is this type of support? This type of support at A is fixed support. Okay, so this is the shape of the fixed support. And how many reaction in a fixed support? How many reaction? We have 3 reactions. We have X, A, Y, A, and because it like restrict rotation, so we have MA. So any fixed support has 3 directions. X direction, XA, YA, and MA. So here I will assume that we have 3 reactions here, and we need to calculate them. We have YA, XA, and MA. Okay, another thing you need to know for this type of beams, the other node should be free. If you have a look here, is there any support at B? Is this B? So this A and this B. B should be free. Okay, so if we have fixed support at one end, the other end should be free. Okay, this type of beams called cantilever beams. So what is mean by cantilever beam? Cantilever beam means a beam with one fixed end and one free end. And in the fixed end, we have three reactions, XA, YA, and MA. Okay? Do you have any problem in this one? So now, I will do it here. Now, this is our beam. And this is the fixed support A, B, and we have a uniform distributed load, 5 kilonewton per meter, and this length is 6 meters. Again, we have the reaction YA, XA, and MA. Okay, the requirement is to calculate shear force and bending moment at point A and B. So we need to calculate the moment here, A, and here, B. Okay, how can we deal with this type of problems? Again, we have two steps. The first step is to calculate the reactions. How can we calculate the reaction? We have three reactions. How can we calculate the three reactions? The first thing is we can deal with the shear, with the uniform load like that. So we need to concentrate the uniform load, UDL. This will be the resultant of the uniform load. How can we find this resultant to deal with the uniform distributed load? If you have UDL over distance L, how can we concentrate this load? First, it will be concentrated in the middle. So L by 2, L by 2. And this resultant, if this UDL is W, so WL. So to concentrate or to get the resultant of a load of a UDL, it will be the UDL value multiplied by the length of the load. Okay, so now how much is the resultant here? In this case, we have 5 kilonewton multiplied by 6 meters, so it will be 30 kilonewton. So the load here or the resultant will be 30 kilonewton. Okay. Do we have any other forces? No. So now to find the reaction, we can apply the equilibrium equation, which is summation x equal to 0. This will give us XA will be 0 because we don't have any horizontal forces. Okay. Okay. Thank you, Shear. The second equation, if we apply summation y equal to 0, What forces in y direction we have? We have YA and 30 kilonewton. Do we have any other forces? We don't. So if we apply summation y equal to 0, we will have YA going up, so positive, minus 30 going down, should be 0. From this equation, we find that YA equal to positive 30 kilonewton. The positive sign means we have assume it correctly and the reaction will be going up. Okay. The last equilibrium equation we have is summation moment at A should be 0. If we apply summation moment at point A equal to 0, this is our point A here. If we are at A, this force pass through, so doesn't have moment. This force pass through doesn't have moment. So what will have moment, or what will cause moment at A? We will have 30 kilonewton and MA. So 30 kilonewton is acting at a distance of 3 meters because it is in the middle. So 3 meters from point A. So if we apply the moment at A equal to 0, we have 30 kilonewton multiplied by the distance 3. And I will give it negative sign. Why negative sign? Because this force is rotating clockwise, so it is negative. So negative because of rotating clockwise, plus MA, and I will give it positive sign because it rotates anti-clockwise. So 30 by 3 plus MA equal to 0. So this gives us MA equal to positive 90 kilonewton meter. The positive sign means the assumption is okay. So now this is our reactions. We have 3 reactions: MA, YA, and XA. Okay, do you have a problem with the reactions? Do you have any problem with the reactions? Okay, now we shift to the next step. The next step is to find shear force and bending moment at A and B. Okay. If we have a look on the beam, our beam, this is our beam, this is the support, and this is the load. And we concentrate the load somewhere here in the middle, 30 kilonewton, and the original load is 5 kilonewton per meter. And we have calculate the reactions, 3 reaction here, 90 kilonewton meter, 0 and 30 kilonewton. And now we need to put the section. We have section here, section A, and here section B. Okay, for this type of beams, we have UDL or uniform distributed load. Is that correct? So in case of uniform distributed load, we have to make different cut from the previous example, because the previous example was point load. Now we have UDL, so we will have 2 sections. Section at the start of the UDL and section at the end of the UDL. So we don't need section in the middle of the UDL for this type, or we will have only 2, as I mentioned, one here at the end and one here at the start. So in any uniformly distributed load, we have two sections. Okay. If we apply section at A, if we make the cut at A, so this is our cut here at A. This section will cut the beam to two sides, one to the right and one to the left. Okay, so now I will work on section A or point A. At point A or section A, we can work from left side or right side. Which is easier for you? I will do it from the right first, so I will do it section A right. Section A from right, if I cut here at A, this section A, and we have, this is the load we have, 30 kilonewton. Do we have any other forces at A, at this section? Only this section. And when we cut at A, what we will find at A? We'll find that we have shear here, QA, and a moment here, which is MA. Okay, so same as we did last example, in the previous example, we will have summation y equal to 0. If we apply summation y equal to 0, we will have QA going down negative minus 30 kilonewton going down negative should be 0. From this, we will have QA is negative 30 kilonewton. So this will be the shear at A. The negative sign means we assume it down and it should be up. Okay. And the next step is to apply summation moment at A equal to 0. If we apply summation moment at A equal to 0, we will have 30 kilonewton. The distance is 3 meters. So if we apply this one, we have 30 kilonewton. Or I will start with the moment first. This moment MA is rotating clockwise, so I will give it negative sign. This one 30 kilonewton is rotating in this direction, so also clockwise, so I will give it negative as well. Negative 30 kilonewton multiplied by 3. These two together should be 0. From this equation, we will find that MA equal to negative 90 kilonewton meter. The negative sign again means the reverse direction. So if I assume MA in clockwise direction, it should be anti-clockwise direction. Okay? Do you have any problem in this one? Okay. Now, I will turn back here. Now we study section A from right side. If I want to make it easier and study it from the left side, what we will have if we study section A? From left side. If you have a look on section A from the left, if this A, because it is very close to the support, so what we will have at A from the right, from the left side, the left side will have only the reaction to the left side. So we'll have YA going up and MA and XA is 0. So we don't have to include XA. So now, if I cut at A and take the left part, so when I cut, there will be QA and MA. Okay. Do you accept this one? Do you accept this one? So we will have shear and a moment at A. So if we know YA is 30 kilonewton up, and we know MA is 90 kilonewton meter. So if we apply summation Y equal to 0, so QA should be minus 30 kilonewton should be 0. So QA should be 30 kilonewton. Okay. And if we apply summation moment at A equal to 0, so MA, this MA should be equal to 90 kilonewton meter. So MA equal to 90 kilonewton meter. This means I just try to make it here again. This means that the straining action or shear at A and moment at A will equal to the reactions. So the shear at A will be the reaction, which is 30 kilonewton, and the moment will be the moment reaction, which is 90 kilonewton meter. This because we are near the support or at the support, so the string action will be equal to the reactions. Okay. Now we can do the last requirement of this beam or this example. He asked us to work on section B. Section B, at the end of the beam here, the free end, this B and this A, and again, this is our reaction, XA, YA, and MA, MA 90, YA 30. We have the load here 5 kilonewton meter, and the resultant is 30 kilonewton. So if we need to calculate at section B here. Section B is dividing or subdividing the beam into two parts. We have part from the right, which is space or nothing here, and part from the left. Which is easier to study from left or right? From left, we have all loads and all reactions. From right, we have space, nothing from the right. So which is easier to study, from left or from right? Do you have idea? Okay, if we study from left, from right, sorry. If we study from right, nothing from right, so Q at B should be 0 and moment at B should be 0. So you should know that at the end of a cantilever, the shear should be 0 and moment should be 0. Okay, so this is as this, you can do it like that, very simple, because we don't have anything here to the right, so the shear 0 and moment 0. But if we start from the left, so from the left, I will do it here. So from the left, you will take all the beam with you, because this is our section B, and this is all the left part. If you study from left, so you have here 30 kilonewton, and you have 90 kilonewton, and you have 30 kilonewton somewhere here because of the uniform load. So when you cut at B, there will be QB and MB. How can we find QB and MB? To find the QB, if we apply summation y equal to 0, so how many forces in y direction? 1, 2, 3. Is that right? So if we apply the equation, so we have 30 going up positive, minus 30 going down negative, minus QB going down. Should be 0. From this equation, plus 30 minus plus 30, so will give us that QB equal to 0. This is the first thing. So QB equal to 0. Again, we apply moment at B. If we apply the moment at B equal to 0, what cause moment at B? First, what this one will not cause moment at B because this is B. So this pass through B, no moment. So all these forces, MB, 30 kilonewton, 30 kilonewton, and 90 kilonewton meter will have moment at B. So if we apply the moment at B, we will have MB negative because positive because clockwise, minus, or this one also positive because it is rotating anti-clockwise, multiplied by 3, minus 30. This 30 is rotating clockwise, so negative, multiplied by 6 because it is clockwise. So this negative, positive, positive. Okay. What else? 90 kilonewton meter is clockwise as well. So 90 kilonewton meter. All of this should be 0. Here you will find that this is plus 90. This is negative 80. This is, so you have something wrong here. Okay, so this one, we are at B, so 30 by 3. This one is 3 meter. So this one, 30 by 3. This is negative 1. This one is positive or negative. This one is anti-clockwise, so this one also positive. This one clockwise, so negative. There's something wrong in this equation, so I have to. Yeah, this one was the opposite direction. Sorry, guys. I just draw it wrongly here. So this 90 in this direction. If we go back, okay, so this one, I will just adjust this one, MA, when we calculate it, it should be in the reverse direction, okay? So the moment here should be in this direction. This is what caused the problem. Okay. So if we go back, just to make a small mistake here, this is the direction of the moment, 90 kilonewton meter, and this is the direction here, 90 kilonewton meter. So this one, 90, will be positive as well because it is anti-clockwise. Okay. So you will have plus 90 minus 180 plus 90. So they will cancel each other. So the moment at B is 0. Okay. So finally, we know that again, without all this calculation, we don't have to do all this calculation. At the end of the beam, the shear and the moment should be 0. But if you want to make sure, or if you want to try it yourself, I include all the loads. So we finally get it as QB equal to 0 and MB equal to 0. Okay. Do you have any problem with this example?